Welcome to this walkthrough on solving LeetCode problem number 1992, find all groups of farmland. In this problem, we'll explore how to locate all contiguous groups of farmland within a 2D grid. Stay tuned as we break it down step by step and discuss efficient approaches to solve it. In this problem, we are tasked with analyzing a 2D grid that represents a farmland. Each cell in this grid contains either a 0, indicating barren land, or a 1, representing fertile land. Our goal is to identify all the rectangular groups of contiguous fertile land, which are made up of connected ones. For each group, we need to determine the coordinates of its top left and bottom right corners. These coordinates are represented as R1, C1, R2, C2, where R1, C1 is the top left corner and R2, C2 is the bottom right corner. Once we identify all the groups, we return their coordinates as a 2D array, with the groups listed in any order. The size of the grid can go up to 300 x 300, and each cell value is guaranteed to be either 0 or 1, making this a well-defined problem. Let's look at an example. Here, the input matrix land is a 3x3 grid where certain cells contain ones. The output for this input is 0, 0, 0, 0, 1, 1, 2, 2. Here's why: the first group of farmland consists of a single fertile cell at 0, 0. Since it is not connected to any other ones, its top left and bottom right corners are both 0, 0. The second group is a 2x2 rectangle of ones, starting at 1, 1, and ending at 2, 2. These two groups represent all the fertile land in the input matrix, so we return their coordinates as the result. Note that the output order does not matter, so these groups can appear in any sequence. In the next example, the input matrix is a simple 2x2 grid filled entirely with ones. The output for this case is 0, 0, 1, 1. Here, the entire matrix forms a single rectangular group of fertile land. The top left corner of this group is at 0, 0, and the bottom right corner is at 1, 1. Since there is only one group, it completely defines the output. Additionally, consider a case with a 1x1 matrix where the single cell contains a 0. Since there are number ones in this matrix, there are no groups of farmland, and the output is an empty list. Now, let's discuss the constraints and additional details. The size of the matrix, defined by m rows and n columns, can go up to 300 in either dimension. Each cell in the matrix will always be a 0 or a 1, and any group of farmland is guaranteed to be rectangular. Contiguity is only defined in terms of rows and columns, so diagonally connected ones do not form a valid group. Furthermore, the output can list the groups in any order, as the problem does not enforce a specific sequence. These details provide clarity on how to approach the problem and ensure that the solution adheres to the requirements. Lastly, it's important to consider various edge cases when solving this problem. For instance, a matrix filled entirely with zeros would result in no groups of farmland, so the output should be an empty list. On the other hand, a matrix filled entirely with ones would produce a single group that spans the entire grid. Additionally, we may encounter groups that span only a single row or column, which are still valid rectangular groups. Finally, we must ensure that the solution performs efficiently for large inputs, such as a 300 x 300 matrix, to handle the upper limits of the constraints. By accounting for these scenarios, we can develop a robust solution to this problem. To solve the problem of finding all groups of farmland in a 2D grid, we need to identify contiguous rectangles of 1s and represent each group using its top left and bottom right coordinates. The first approach we considered is a brute force, iterative check. Here, we traverse through every cell in the grid, and when we encounter a 1, we expand outward to find the full rectangle by iterating to the right and downward until we hit a 0 or the edge of the grid. As we identify the boundaries of a rectangle, we mark all the cells within it as processed to avoid redundant checks. While this approach ensures that we eventually cover all farmland groups, it involves repeated boundary checks for each one, making it less efficient for larger grids. Another approach is to use depth-first search (DFS) or breadth-first search (BFS), treating the problem as a connected component search. This method systematically explores all connected 1s to find the rectangular boundaries of each farmland group. With DFS or BFS, the steps involve starting a traversal for every unvisited one and exploring all its connected 1s while keeping track of the minimum and maximum row and column indices. These indices define the boundaries of the rectangle. As the traversal progresses, we mark all visited cells as processed to avoid revisiting them. This ensures that each cell is processed only once, resulting in a time complexity of O(n*(m). The space complexity is O(n*(m) in the worst case because of the recursion stack in DFS or the queue in BFS. This approach is efficient, especially for sparse grids, as it avoids duplicate processing. Another optimized method is a greedy grid scan. Here, instead of using DFS or BFS, we perform a single pass over the grid. When we find a 1, we immediately expand downward and rightward to determine the rectangle boundaries, marking all the cells within the rectangle as processed in one operation. This method is highly memory efficient because it doesn't require additional data structures like stacks or queues, and it works well when the farmland groups are clearly rectangular. However, it is less adaptable to irregularly shaped groups. We ultimately chose the DFS approach because it balances clarity, simplicity, and adaptability. While the greedy single-pass method is more memory efficient, it is less intuitive for handling irregularly connected farmland groups, even though the problem guarantees rectangular shapes. With DFS, we can systematically traverse all connected 1s, dynamically calculating the boundaries of each rectangle. This ensures correctness while remaining easy to implement. A key observation is that farmland groups being rectangular simplifies boundary calculations significantly. By marking cells as visited during DFS, we prevent redundant processing and streamline the exploration. The trade-off, however, is higher memory usage due to the recursion stack compared to the greedy approach. Despite this, the systematic nature of DFS makes it scalable and reliable for a wide range of grid configurations. Therefore, it offers the best balance between computational efficiency and implementation clarity. To tackle the problem of identifying all groups of farmland in a 2D grid, we need a structured approach. First, we start by parsing the input, which is a 2D grid called land. In this grid, a cell value of 1 indicates farmland, while 0 indicates non-farmland. The ultimate goal is to identify and return all contiguous rectangles of farmland, with each rectangle represented by its top left and bottom right coordinates. To achieve this, we initialize an empty list called result, which will store the identified rectangles. Additionally, to ensure we do not process the same cell multiple times, we create a visited array of the same dimensions as the grid, with all values set to false. The algorithm uses a nested loop structure to traverse each cell in the grid. For every cell at position i, j, we check if it is farmland, i.e., if land I, j equals 1, and if it has not yet been visited. This forms the basis for isolating new farmland groups that we can explore further. When we find an unvisited farmland cell, we initiate a breadth-first search, or BFS, to explore all connected farmland cells. BFS is particularly suitable here because it systematically explores all neighbors of a cell before moving outward. To implement this, we use a queue and start by adding the initial cell, I, j, to it, marking it as visited. At the same time, we maintain 4 variables, top, left, bottom, and right, all initialized to the coordinates of the starting cell. These variables will help us track the boundaries of the rectangle enclosing the farmland. As we process the queue, for each dequeued cell, x, y, we examine its neighbors in all 4 directions, up, down, left, and right. If a neighbor is valid, meaning it is farmland and unvisited, we add it to the queue and mark it as visited. While doing so, we also update the rectangle bounds, adjusting top, left, bottom, and right as needed to encompass the newly discovered cells. Once the queue is empty, we know the rectangle bounds for this group of farmland, and we append the tuple, top, left, bottom, right, to the result list. This ensures we accurately capture the extent of the farmland group before moving on to other unvisited cells. After processing all cells in the grid, the algorithm returns the result list containing the top left and bottom right coordinates of all identified rectangles. This efficient process ensures we systematically find and store every group of farmland. BFS plays a crucial role here because it allows us to comprehensively explore connected regions, ensuring no farmland cell is missed. By tracking the top, left, bottom, and right bounds during BFS, we can determine the enclosing rectangle for each group without needing additional passes over the grid. The visited array is equally important because it prevents redundant processing of cells and avoids potential infinite loops. These key insights, systematic exploration with BFS, boundary tracking with rectangle bounds, and avoiding redundancy with a visited array, form the backbone of the algorithm, making it both effective and efficient. The algorithm relies on three critical data structures. First, we use a queue to implement BFS, which allows us to explore connected cells level by level. The operations on the queue, such as enqueue and dequeue, are performed in constant time, ensuring the traversal remains efficient. Second, the visited array is a 2D Boolean structure that keeps track of which cells have already been processed. Its size matches the dimensions of the grid, and its space complexity is proportional to m*n, where m and n are the grid dimensions. Finally, the result list serves as the output container, storing the coordinates of all identified rectangles. These data structures work together seamlessly to ensure the algorithm processes the grid systematically and efficiently. When analyzing the algorithm's complexity, we observe that the time complexity is O(m*n), where m and n represent the grid's dimensions. This is because each cell is visited exactly once, and its neighbors are checked in constant time. The space complexity is also O(m*n), which accounts for the visited array and the BFS queue in the worst-case scenario. It's important to consider edge cases as well. For instance, if the grid is empty, the output should simply be an empty list. If there is no farmland at all, meaning all cells are 0, the output should also be an empty list. For a single-cell grid, such as 1, the output should correctly identify the single rectangle as 0, 0, 0, 0. These considerations ensure the algorithm handles both typical and edge cases robustly. The algorithm is also well equipped to handle scenarios where farmland does not form perfect rectangles. For irregularly shaped connected regions, the BFS ensures that all connected cells are explored and the rectangle bounds are adjusted dynamically to enclose the entire group. This means that even if the farmland extends in an uneven or non-linear fashion, the algorithm will still calculate the correct top left and bottom right coordinates for the enclosing rectangle. The versatility of this approach makes it robust for a variety of grid configurations, ensuring accurate and consistent results regardless of the farmland's shape. Here, we define a class solution with a method find farmland that takes a 2D grid land as input. This grid represents the farmland, where a value of 1 indicates farmland and 0 indicates non-farmland. First, we determine the number of rows and columns in the grid and initialize an empty list result to store the coordinates of each farmland group. Next, we define a helper function DFS to perform depth-first search. This function takes the starting coordinates of a cell and explores the entire connected group of farmland cells. Inside DFS, we initialize the bottom and right boundaries of the farmland to the starting cell. We use a stack to iteratively explore the connected cells, marking each visited cell by setting its value in the grid to 0. For every cell we visit, we update the bottom and right boundaries to ensure they encompass the entire farmland group. We also check all 4 possible directions: right, down, left, and up, ensuring we stay within grid bounds and only visit unvisited farmland cells. Once all connected cells are processed, the function returns the bottom right coordinates of the farmland group. Now, we iterate through the grid using 2 nested loops to check every cell. If a cell contains a 1, it means we've found the start of a new farmland group. We mark the cell as visited by setting it to 0, then call the DFS function to explore the entire farmland group. The DFS function returns the bottom right corner of the group, and we append the coordinates of this farmland group, top left and bottom right, to the result list. Once all cells in the grid are processed, we return the result list, which contains the coordinates of all farmland groups in the grid. In this implementation, we start by defining the find farmland method, which takes a 2D array land as input. The variables rows and cols store the dimensions of the input grid, and we initialize a result list to hold the coordinates of farmland groups. To help us traverse the grid and group connected farmland cells, we define a helper method DFS. This method uses depth-first search to explore all cells in a connected farmland group, starting from a given cell, R, C. A stack is used to facilitate this exploration, and as we traverse, we update bottom and right to track the furthest boundaries of the group. The for loop inside the while iterates through all possible directions: right, down, left, and up, checking if the neighboring cell is within bounds and part of a farmland group, i.e., it contains a 1. If so, we mark it as visited by setting its value to 0 and add it to the stack for further exploration. When the stack is empty, meaning all cells in the connected group have been visited. The DFS helper method returns the bottom right boundary of the group as an array. Now, we iterate over each cell in the grid using nested for loops. If we encounter A1, it indicates the start of a new farmland group. We mark the cell as visited, call the DFS method to find the boundaries of the group, and add the coordinates of the top left and bottom right corners to the result list. Once all cells have been processed, we convert the result list to a 2D array and return it. This ensures that all groups of farmland are identified and their boundaries are correctly formatted for the output. To solve the problem, we start by analyzing the given input, which represents a grid of land cells. Each cell can either be 1, indicating farmland, or 0, indicating non-farmland. In this example, the grid has 3 rows and 3 columns. We initialize 2 key variables, result, and empty list to store the coordinates of each farmland block, and rows and calls, which represent the dimensions of the grid. The outer loop begins at the first row, I equals 0, and the inner loop starts at the first column, j equals 0. As we iterate, we find that land, 0, 0, is 1, meaning we've identified the start of a farmland block. We mark it as visited by setting land, 0, 0, to 0, then initiate a depth-first search, DFS, to explore the entire farmland block starting at this cell. The DFS is initialized with a stack containing the starting cell, 0, 0, and 2 variables, bottom and right, which will track the bottom right boundary of the farmland as we explore further. During the DFS, we begin by popping 0, 0 from the stack and checking all its neighboring cells. The cell 0, 1 is valid farmland, so we mark it as visited by setting land 0, 1 to 0 and add it to the stack. Similarly, the cell 1, 0 is valid farmland, so we mark it as visited and add it to the stack. At this point, we update the bottom and right boundaries to 1 and 1, respectively, because these represent the farthest row and column of the farmland block we've encountered so far. As we continue processing the stack, we pop 1, 0, and 0, 1 and mark their neighbors, but no new farmland cells are found, so the DFS concludes. The bottom right boundary of the block is determined to be 1, 1. We append the coordinates of this farmland block, 0, 0, 1, 1, to the result list. The outer loop then continues, but since all other farmland cells in the grid have been visited or marked as 0, no further blocks are identified. The final output for this example is 0, 0, 1, 1. In the second example, the grid is slightly larger, with 3 rows and 4 columns, and contains 2 distinct farmland blocks. We initialize rows, calls, and result as before. The outer loop starts at I equals 0, and the inner loop begins at j equals 0, where we find land, 0, 0, is 1, marking the start of the first farmland block. We set land, 0, 0, to 0 and call DFS. The DFS stack is initialized with 0, 0, and the bottom and right boundaries start at 0. As we explore neighbors, 1, 0, is marked visited and added to the stack. The bottom boundary is updated to 1. The DFS completes for this block, and we determine its bottom right boundary as 1, 0. The coordinates 0, 0, 1, 0 are appended to result. Continuing the inner loop, we reach j equals 3 and find another one, identifying the start of a new farmland block. We mark land 0, 3 as visited and call DFS again to explore this second block. For the second farmland block, the DFS starts with the stack containing 0, 3. The bottom and right boundaries are initialized to 0 and 3, respectively. As we explore, the cell 1, 3 is valid farmland, so we mark it as visited and add it to the stack. The bottom boundary is updated to 1, while the right boundary remains at 3. The DFS concludes after visiting all farmland cells in this block, and the bottom right boundary is determined to be 1, 3. We append the coordinates 0, 3, 1, 3 to the result list. After completing the outer and inner loops, no additional farmland blocks are found, so the final output for this example is 0, 0, 1, 0, 0, 3, 1, 3. This demonstrates how the algorithm can handle grids with multiple disjoint farmland blocks, accurately identifying and recording each one. In the final example, the grid contains no farmland at all, as every cell is 0. The initialization step sets up rows, calls, and result as usual, but as the outer and inner loops iterate over the grid, no cells with a value of 1 are found. Since all cells are 0, there are no DFS calls, and the result list remains empty throughout the execution. The algorithm correctly determines that there are no farmland blocks, and the final output is simply an empty list. This example highlights that the algorithm handles edge cases effectively, such as when the grid contains no farmland at all. The time complexity of our solution is driven by the depth-first search traversal of the grid. Let's break this down step by step. First, we have the outer loop, which iterates over every cell in the grid. If the grid has rows and calls columns, this iteration happens rows*calls times, making it rows*calls. Next, for any cell that represents farmland, where land, I, j, equals 1, the DFS is triggered. The DFS explores all connected farmland cells, marking them as visited. Importantly, each farmland cell is processed exactly once throughout the traversal. In the worst-case scenario, where every cell in the grid is farmland, this would mean the DFS operates on all rows multiplied by all columns, or rows*calls. Combining the outer loop and DFS, the overall time complexity is rows*calls. This time complexity is efficient because each cell is visited only once, either during the outer loop or through the DFS traversal. Now let's analyze the space complexity. The space usage can be broken into 3 parts. First, the DFS stack, which stores cells to be explored. In the worst case, the depth of this stack equals the size of the largest contiguous farmland group, which can grow to M, where M is the size of that group. Second, the grid is modified in place to mark cells as visited, so no additional space is required here. Third, the result list stores the coordinates of each farmland group. If there are G groups, the space required is G. In the worst case, where every cell is its own group, this would also be rows*calls. In practice, the space complexity depends on the scenario. For average or best cases, the DFS stack, which is M, is the dominant factor. However, in the worst-case scenario, the result storage can dominate, leading to a space complexity of rows*calls. To compare, a brute force approach might involve checking all possible rectangular farmland groups explicitly. This would lead to a time complexity of rows*calls, 2, as many cells would be revisited unnecessarily. In contrast, the DFS-based solution optimizes this by processing each cell only once. By marking cells as visited and exploring connected groups efficiently, the time complexity is reduced to rows*calls, making the solution far more efficient and scalable for larger grids. Now let's consider the best, average, and worst-case scenarios. In the best case, the grid contains no farmland cells, meaning no DFS is triggered. The outer loop handles all cells in rows*calls time, while the space complexity remains constant at 1. In the average case, the grid has a mix of farmland and non-farmland cells. Each farmland group triggers a DFS, but the time complexity remains rows*calls, while the space complexity depends on the size of the largest farmland group, which could vary significantly. Finally, in the worst case, all cells are part of one large contiguous farmland group. Here, the DFS explores the entire grid, leading to a time complexity of rows*calls and a space complexity of rows*calls due to the stack. To confirm the big O analysis, let's summarize with a mathematical proof. Each cell in the grid is visited exactly once, whether during the outer loop or through the DFS traversal. This means the total work is proportional to the number of cells, which is rows*calls. Furthermore, operations like marking cells as visited or adding them to the stack occur in constant time, 1, for each cell. On the space side, the largest farmland group determines the maximum DFS stack depth, while the result list grows proportionally to the number of farmland groups. Both are bounded by rows*calls in the worst case. Therefore, the overall time complexity is rows*calls, and the space complexity is also rows*calls in the worst case. When solving this problem, there are a few common mistakes you should be aware of. First, not marking visited cells is a frequent issue. If you forget to mark cells as visited, your algorithm may revisit the same farmland group multiple times. This can lead to infinite loops in certain implementations or significantly increase runtime by processing the same area repeatedly. To avoid this, ensure that each cell is marked as visited either by modifying the grid directly, like setting the cell to 0, or by using a separate visited array. Another mistake is assuming all farmland groups are irregular shapes when the problem explicitly guarantees that they are rectangular. Misunderstanding this can lead to overcomplicated logic and unnecessary computations. Stick to the rectangular assumption to simplify your solution. Finally, using inefficient search techniques, like repeatedly scanning the entire grid for unvisited 1s, can result in a cubic time complexity of n cubed. Instead, take advantage of the connectivity of farmland groups to optimize your search to n*m. Another error to watch for is incorrect bounds handling. When expanding the rectangle to find the bottom right corner of the farmland, you need to carefully account for all neighboring cells. Missteps here can cause you to miss parts of the group or accidentally include extra cells outside the rectangle. This results in incorrect group definitions. Additionally, overlooking edge cases can cause pitfalls. For example, grids with no farmland at all, single-cell grids, or groups that touch the boundary of the grid all need to be handled explicitly. Without addressing these scenarios, your code might encounter runtime errors or produce incorrect results. Always test your solution against these edge cases to ensure robustness. This problem is fundamentally a connected components problem in a grid, which means techniques like depth-first search, breadth-first search, or even union find can be applied. Of these, DFS and BFS are more straightforward for this problem. It's helpful to recognize patterns in grid traversal problems, as they frequently appear in interviews. Problems involving connected components, like flood fill or island detection, share many similarities with this one. A key optimization focus here is ensuring each cell is processed only once. For large grids, this is critical to keeping the algorithm efficient. When discussing this problem in an interview, always confirm assumptions with the interviewer, such as whether all farmland groups are guaranteed to be rectangular. Misunderstanding these guarantees can lead to overly complex solutions. Finally, related problems like LeetCode 200, 695, 463, and 733 provide excellent practice for mastering the core techniques used here. There are several approaches you can use to solve this problem. Depth-first search, or DFS, involves starting from an unvisited one and recursively exploring its neighbors to determine the boundaries of the rectangle. While simple to implement, DFS can lead to stack overflow in very large grids due to recursion depth limits. Breadth-first search, or BFS, avoids recursion by using a queue to explore neighbors iteratively. It efficiently tracks boundaries while marking cells as visited, but it may use more memory because of the queue. Another option is iterative grid traversal with nested loops. Here, you directly calculate rectangle boundaries by scanning rows and columns whenever an unvisited one is found. This approach is more memory efficient than DFS or BFS but can be less intuitive and harder to debug. Each method has its trade-offs, so choose the one that best fits the constraints and requirements of the problem. Great job following along. To recap, we applied search algorithms like DFS or BFS to solve a 2D grid traversal problem efficiently. Remember, mastering these techniques is critical for interview success. Don't forget to like, subscribe, and stay tuned for more coding solutions. Thanks for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!